Assalamualaikum, we are from Group 4. My name is Noor Ashikin, my other member is Raja Nur Shafini and Nordina Nadia. We will be presenting on the topic RQ stock replenishment in multi-mode distribution system with a certain delivery channel and additive channel allocation. I will start first with introduction. In supply chain, uncertainty is common due to factors such as natural disasters, strikes, or policy changes such as COVID-19 lockdown. This event can affect both demand and delivery. Currently, to handle this, companies use multi-mode distribution such as train, truck, or express delivery to improve robustness and reduce costs. Finally, the main goal is to prove mathematically that the RQ policy robust under dual uncertainty, both demand and delivery, and introduce dynamic channel allocation strategy. Next, I will explain the problem statement. The main challenge in this study is that the system faces two major uncertainty. First, demand is unknown and it can change at any time in unpredictable way. Second, delivery delay are inconsistent because they differ across distribution channel and can also shift unexpectedly. So because of the uncertainty, the paper aimed to develop and test inventory control strategy using the RQ replenishment policy. So the goal are to ensure all customer demand is satisfied, to avoid back order or the need of emergency storage, and finally to reduce holding costs.
I'm Nordina Nadia binti Muhammad Fuad. My metric number is 157690. First of all, I will go through quickly about our flow in this assignment. First, we study the problem regarding RQ policy that involve in RQ stock replenishment in multi-mode distribution systems. And then we identify the concept of methodology that involved in the case study, which is system model, stock replenishment policy, policy format analysis, and dynamic channel allocation strategy. And then we discuss the analysis of result based on dynamic allocation, static allocation, variability with dynamic allocation, and efficiency of dynamic strategy. And lastly, we make conclusion and suggestion for future work. So, this is the notation needed in this study, and I will explain more regarding these 4 parts of methodology in the next section. Let's begin with system model. This model shows the structure of how goods flow through the supply chain, where first, supplier will dispatch all the goods, which denote as QT. Then it will go through lot partitioning, where lot partitioning is a strategy to divide a shipment into several parts and sending them using multiple delivery channel. And then the goods will go through with multiple channel, which is like here is 1 until N. And then sometimes some of the goods will go through delay. Delay is like the transportation time between supplier and depot or the waiting time at the depot. After that, the depot will serve the market demand, which denote as TT. Stock update equation is the core equation for our inventory system. It shows how the stock level at the depot update each time. First, we start with current stock, which is XT. Then we add all the goods that arrive at the depot in the current time period. Finally, we subtract the customer demand, which is will reduce the stock. For methodology 2, which is stock replenishment policy, it is a rule that tells us when to order and how much to order to refill the stock at the depot when it gets low. So, this is what RQ policy are about. So, RQ policy defined by this QT equation. This equation means whenever the inventory position falls below or equal to the order point, we will send a shipment of size Q. This helps us maintain stable stock level, avoid stock out and overstocking, and react to inventory change using real-time information. Next is the policy format analysis, which gives us confidence that our RQ strategy works. There are 2 theorems in policy format analysis. Theorem 1 is bounded stock at the depot. It means our depot will never exceed its capacity. Theorem 2 is sufficient stock to meet demand. If the reorder point is set greater than or equal to QA plus Q plus E, we can prevent stock out and we can guarantee service even under uncertainty. So these 2 equations protect us from having too much stock or overflow and protect us from having too little or stock out. Lastly, dynamic channel allocation strategy. So it is a strategy that adjusts how shipments are split across multiple delivery channels in real time based on each channel delay performance. So this is the equation for dynamic channel allocation strategy. It contains the total shipment and fraction assigned to that channel. So this strategy adjusts the fraction assigned to each channel in real time based on how fast or delay each channel is, which it will send more through faster channel and send less through delay or unreliable channel. This matter because it reduces delivery delay, balance the load across channel, improve timing of arrival, and help the system respond dynamically to actual delivery channel.
The case study that we'll discuss is about dynamic allocation and static allocation. The aim of dynamic allocation is to optimize stock replenishment with lambda I in time that change with delay conditions in real time, while static allocation have a fixed lambda, which is fixed lot fraction. Let's look at for the scenario of the case study, where they have one supplier, one depot, and three delivery channel, which each channel has a different delivery time and reliability. As you can see, channel 1 is about train line, channel 2 trucks, and channel 3 is small truck express delivery. Every channel have their own details about nominal delay, delay uncertainty, lot size, lot fraction, and delay tolerance. The scenario gives demand with 110 units, lot size 120 units. The demand fluctuations is as follows. Reorder point 1030 units, then based the information, we got depot capacity equal to 1350 units. Okay. The purpose of this scenario is to show how dynamic allocation reduce depot stock and holding costs without any back orders. The result that we can get from previous scenario is about channel delay that shows the fluctuations in channel delay where involve channel 1, channel 2 and channel 3. As we can see, channel 1 has a longer average delay than channel 2 but less variation in jitter in its delays. Next, inventory position of static channel allocation and dynamic channel allocation. It shows total available goods that from on hand plus in transit. Then as we can see, both strategies is trigger new orders at the same or nearly the same times. It means inventory is always sufficient to meet demand. Last but not least, the result is about depot stock level for static channel allocation and dynamic channel allocation. The figures show goods physically stored at the depot over time. Dynamic show lower stock that proves cost is efficiency, and we can see that the pattern of the graph still never hits zero. That means no stock out, no back orders, and demand is fully satisfied. This leads to a holding cost reduction as follows. From analysis of result, the RQ policy ensures that stock is replenished efficiently, preventing both stockouts and excess inventory. For dynamic allocation, it adapts to demand and delivery change, leading to lower stock levels and reduced holding costs while ensuring all demand is met. For static allocation, it follows a fixed strategy leading to higher stock levels and increased costs and inefficient storage use. Last but not least, for efficiency of dynamic strategy, the dynamic allocation is more efficient, cost-effective, and resilient in managing uncertain demand and delivery delays.
For the conclusion, the RQ arbitrary policy analytically proven robust in multi-mode uncertain system. They assure no emergency storage needed means that we can save space and resource. Second, no demand loss means that customer needs are fully met. Lastly, we can reduce costs with adaptive strategy. For the future words, first, future world could explore additional control policies such as out, order up to policy. Second, the model could be extended to incorporate lateral transshipment. This feature can allowing goods to be moved between depots for more flexible supply chain management. Lastly, real-time adaptive system could be developed to dynamically adjust replenishment strategy based on live data from the supply chain. This is our task distribution for each member.